Okay, hi everyone. We're talking about our last topic in chapter 2, thermochemistry. And there's really two questions that I want to answer. The first is right here. Given a set of specified conditions, how do we determine delta H for a chemical reaction or physical transformation? Physical transformation means phase change. Second question is a complement to that. If I now have a specified chemical reaction, how do I determine delta H under a different set of conditions? Specifically, temperature is what we're interested in. In this video, I'm going to talk about the first question. And the first thing that we need to talk about is this set of specified conditions. What do I mean by that? There we go. So the specified conditions that we talk about are called standard conditions. Standard is a technical name. It means the pure form of a substance at 1 bar, and the temperature is typically 25 degrees C unless otherwise specified. The way that we indicate that something is in the standard state, or refers to a standard state, is with this degree symbol. So when you see the degree symbol, that means standard state. Once I've defined what those specific set of conditions are, I can now figure out how to get the thermodynamic data. Right? How do I calculate delta H for some reaction? And here's my answer. Okay. The way you find this thermodynamic data is one of two ways. The first is you can simply look it up. Right? I'm going to suggest to you that the Atkins textbook, CRC handbook, the NIST chemistry web book are all really good places to find thermodynamic data. I think it's always a good idea to be wary of Wikipedia. I've seen countless errors on Wikipedia, so be a little wary of that. Although I suppose there's errors in these things too. But anyways, here's an example from Atkins. Table 2C1. This is listing the standard enthalpy of fusion and vaporization for various molecules. This 7 symbol you can ignore. Let's see. For whatever reason, this thing should have printed as just the degrees symbol. These are the standard enthalpy of transition. And so, for instance, in the case of water, this is telling me at 1 bar, it takes 6 kilojoules to melt 1 mole of water. I didn't say this, but fusion means melting. Right? At 1 bar, it takes 41 kilojoules, or 44 kilojoules, to vaporize 1 mole of water. So you can simply look this data up in a reliable text. What if you can't look it up in reliable text? Well, what you do in that case is to use Hess's law to determine it from given data. So I'll give you some examples of this, and you'll know Hess's law. It's a gen chem concept. But what Hess's law says is that I can take the individual steps of a reaction, add up the delta H's, and I get delta H total, right? So the standard enthalpy of the overall reaction is the sum of delta H for the individual steps. And this manifests itself in a couple different ways. So for instance, I'm given data here for fusion, for melting, and for vaporization. What if I wanted some other data, like delta H freezing? Well, here's how you can think about that. Pen. Remember that H is a state function. So I can draw it on a number line. Here's the enthalpy of the solid. Here's the enthalpy of the liquid. If I'm wondering about delta H of fusion, of melting, that's this, solid to liquid. Delta H of freezing is this, delta H. Trust me, that says freezing. So the answer is that delta H of freezing equals negative delta H of fusion. They're equal and opposite. What if I wanted sublimation? Well, solid liquid, you might imagine that the gas is someplace up there. Right? This is delta H vaporization, go from a liquid to a gas. So in order to get delta H sublimation, you could simply add together delta H standard diffusion, delta H standard of vaporization. Right? So pretty simple ideas. H is a state function. I can just add them up, I can flip it around, and it all works. There are other versions of this problem. Calculate delta H of the reaction. R there stands for the reaction. For this, given these individual steps, I'm not going to go all the way through this. Hopefully this is stuff that you know from Gen Chem, but you flip the reaction around and solve some things. I'll put this up as a worksheet problem. Hopefully you know how to do this stuff. But what I really want to ask is, I think, a more relevant question, something you might not be as familiar with. And that is this. You know, I could imagine calculating delta H for this reaction, provided I have these individual steps. But what happens if I don't have the intermediate reaction steps? These are kind of can't be problems because it assumes that you have this individual steps. What happens when you don't have those steps? Well, here's the answer. It turns out that thermodynamic data, I'm going to move my screen over just a hair. There you go. Thermodynamic data has been generated for a set of reactions that can be applied to any molecule. These reactions are called formation reactions. Once I have formation reactions, I can use them to generate reaction enthalpies for any arbitrary reaction. Okay? So let me try and show you what I mean by this. Here's that same problem. Calculate delta HR for this reaction. What you might imagine doing is taking the reactants, okay, in this case something like PCl3 and chlorine gas. Imagine that I took this PCl3 and I broke it apart to produce some hypothetical compound which is just pure phosphorus and pure chlorine. And then I took this other reactant, chlorine, and I somehow transferred this to a pure chlorine state. This is kind of dumb because it already is pure chlorine. But if I had pure phosphorus and pure chlorine, you could imagine that I could flip those around and combine them to get pure PCl5. And if I did all of this sort of in the right amounts and with the right types of stuff, these would all cancel, right? And you'd be left with the overall reaction. These types of reactions are the formation reactions, right? So we're taking our molecule and we're breaking it up into some hypothetical construct, right? All right. So this hypothetical state where we're breaking things up to actually has a technical name, which is called the reference state. The reference state of an element is its most stable state of the pure compound at the specified temperature in 1 bar, right? So let me give you some examples. I could ask a question of what is the reference state for carbon? And so what you have to ask is, well, what's the most stable form of pure carbon at 1 bar? And you may or may not know this, but it turns out to be graphitic carbon, right? That's the most stable form of carbon at 1 bar. What about oxygen? Well, at 1 bar, oxygen exists as a gas. And so the reference state for oxygen is O2 gas. Hydrogen, H2 gas, right? These are all examples of reference states. They're the most stable form of it in a pure compound at 1 bar. If I have these definitions, I can then use them to formally define enthalpies of formation. So the enthalpy of formation is the standard reaction enthalpy for the formation of a compound from its elemental constituents in their reference state. This is formally what a formation reaction is. And let me give you an example. Let's say I wanted to write the formation reaction for benzene. So when you make these, you make the compound. This is always going to be the product. Okay, so we're going to make C6H6 liquid. And the question is, what are the reference states of carbon and hydrogen? Well, we just talked about that, but it's going to take 6 carbon solid plus 3 H2 gas. And if I do all that right, I can get 6 C6H6, right? Benzene liquid. This is the formation reaction for benzene liquid. When I put all of this together at the end of the day, I end up with this important equation. And if you're a kind of person who's taking notes, write this in your notes and circle it. Delta H of reaction is equal to delta H of formation of the products minus delta H of formation of the reactants. Another common way you'll see this written is as follows, right? Delta H equals the summation of V sub J delta H of formation J. So this variable right here, V sub J, is the stoichiometry number of reagent J. You may or may not remember from your Gen Chem, but stoichiometry numbers are unitless numbers. They have no units. And by convention, they are positive for products and negative for reactants. So to give you one example, phosphorus here is a reactant, so it is negative, and the stoichiometry number is -2. Chlorine is a reactant, stoichiometry number is -3. PCl3 is a product, stoichiometry number is +2. With that notation, you can calculate delta H of reaction for any reaction that you want using formation reactions. All right, there'll be some example problems, check them out, and I will see you next time to talk about question 2. Peace.